Okay, so this experiment is on RTD or residence time distribution. So you have already covered it or studied it in the CRE1 course. So, and you have the idea about the residence time distribution. So it is nothing but
Hello, ma'am.
residence time distribution is characterizes the mixing pattern um, which occurs in the reactor because say in case of black flow we assume that there is no mixing component or dispersive component present in the system, so that is for ideal PFR. And also in case of CSTR, we assume that the system is perfectly mixed. So both of them are not fully correct in case of the real reactors. So, for the determination of this residence time distribution, we use some tracer, and the characteristic of tracer is that it is non-reactive in nature because this RTD has nothing to do with the reaction. It is actually the characterization of the behavior of the reactor from the perspective of hydrodynamics. Now, and we also know that these RTD experiments can be conducted by introducing tracers in different modes. That is, it may be a pulse type input, it may be a step input. So, this experiment uses a pulse type of introduction of the this tracer in the system.
हेलो मैम।
बोलो। बोलो। लैब चल रहा है मेरा, बोलो। नहीं, लैब हो रहा है मेरा। हेलो। हेलो। हेलो।
এখন কি শুনতে পাচ্ছ? ক্যান ইউ হিয়ার মি নাও?
यस मैम।
यस मैम।
ওকে, ওকে।
ম্যাম অনেকে ঢোকার চেষ্টা করছে, একটু অ্যালাউ
কোন
করুন।
অবধি তুমি তোমাদের
ম্যাম সবে
কোন
ম্যাম
জায়গা
সবে
থেকে আমি
আরটিভিটা
ডিসকানেক্টেড
ম্যাম
হয়ে
সবে
গেছিলাম?
আরটিভিটা বলতে স্টার্ট করেছিলেন যে আর ট্রেসার ক্যারেক্টারিস্টিক্স কি হয় ওগুলো যে স্টার্ট করেছিলেন বলে।
এটা এখানে?
হ্যাঁ 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 হ্যাঁ, একদম ফার্স্ট পেজে এই ট্রেসারের ক্যারেক্টারিস্টিক্স গুলো
ও,
বলছিলেন।
ওকে। So this is the
হ্যালো ম্যাম,
characteristics.
ম্যাম অনেকে ঢোকার চেষ্টা করছে, একটু অ্যালাউ করে দিন।
Huh? Huh?
ম্যাম অ্যাটেন্ডেন্সটা কি নোট করে নেব?
And you know,
ওকে।
আর তো কেউ নেই, আর তো কাউকে দেখতে পাচ্ছি না ঢোকার চেষ্টা করছে। So here, this is the residence time distribution which characterizes the mixing pattern of this chemical reactants within the this reactor, because as we know that in case of ideal PFS, there is no dispersion ideally present, and that's why all the reactant molecules have the same residence time. And for that, this how much is the non-ideality in the reactor, we have to go for this residence time distribution experiments. And to conduct these RTD experiments, we have to use tracer, which are non-reactive components. And what is done is this tracer is introduced to the reactor in either through pulse mode or through step mode. So, and here we are using the pulse mode of experiment. So, injection is done at this position at the inlet, and samples are taken at the outlet, and this concentration of the tracer is measured and in the outlet samples. So here, and what is this? And we know that in case of pulse input, we introduce a certain amount instantaneously, and this the amount or this tracer material amount of the tracer material within the T and T plus delta T, this tracer material leaving the reactor is can be obtained by Ct into V into delta T. So the fraction of the material which has resided from the time t and t plus delta t is nothing but delta t divided by n0. Now n0 is the amount of tracer which has been introduced to the reactor at the initial moment, and this is nothing but if you integrate vct dt in the limit of 0 to infinity, you also get the value of n0. Now, the thing is, it is not possible for anyone to maintain infinite or allow infinite time. So, this experiment is conducted up to a time when this outlet concentration drops to zero. Outlet concentration of the tracer drops to zero. Now, here, what you can do is this, you can determine the value of ET. So ET is nothing but this one. So V into CT by N0. And so it is nothing but if you compare this with this form, here delta n by n0. So from this, you can see that delta n by n0 is nothing but Et into delta t. So, and from this concept, you can also determine the value of this Et, and which is nothing but the residence time distribution function. And this Et is nothing but Ct divided by integral of Ct dt. Now the thing is, you will take samples at different intervals, and you will also determine the concentration of the tracer in the sample. So you will have the values of concentration against time. And So for that, you can determine this denominator by this numerical integration. You can apply Simpson's rule and you can evaluate integral of CTDT. Only thing is, as we cannot allow infinite time, so only thing is the time for which this experiment is run, that will replace the upper limit. That is, instead of infinity, it will be the time for which we have conducted the experiment. Now you know that there are some moments of the RTD. So first moment of RTD is nothing but mean residence time. So it is nothing but Tm. This is integral of t e t dt in the limit 0 to infinity divided by integral of e t dt in the limit 0 to infinity. Now, this one, integral of e t dt, that is, you are summing up all the fractions here, and this is nothing but 1. And so, Tm is nothing but integral of t e t dt in the limit 0 to infinity. And similarly, this variance, which is nothing but the second moment of RTD, this one is sigma square, that is equal to integral of t minus tm whole square et dt, and in the limit 0 to infinity. And as I have told you, this infinity, the allowing of infinite time is not possible. So this is the time of the experiment, uh, which is allowed when, up to the point when the outlet concentration of the tracer reduces to 0. So you will see here what we have done is this. So these are the results for the flow rate of 5 LPH. So we have introduced here that we have maintained the flow rate of 5 LPH here, and what we have done, we have injected 5 ml of 10 normal sulfuric acid into the at the inlet position, and we have withdrawn 10 ml of sample from these points. And what is done, and this at the these outlet samples are taken at different intervals. You can see what are the intervals of sampling. So 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Up to this 1 minute interval is maintained, and after that 2 minutes interval is maintained up to the point when the this outlet concentration has dropped to 0. So these are the results, and using these results, you can calculate. And we have titrated these samples against n by 10 NaOH, and you have been given with the titer values, which are in ml again. So Ct, this is nothing but Vt times n by 10 divided by, or you can just write 1 by 10 because you are um, writing it in mole per liter, so which is nothing but n. So 1 by 10 divided by 10 ml of sample you have taken. So you can determine Ct from these experimental results, and using these you can furnish this table. So here this CTDT you can calculate in terms of gram per liter also, and you can also determine the value of ET as well as the value of the variance. And the thing is, you know that when we plot CT against T, it is known as the C curve, and when we plot ET against T, it is known as the E curve. So you have to draw the C curve, E curve, and also you have to determine the the variance for from the values from the experimental values which are being provided to you. Now I'm running the video where from you can have the idea of this. Tubular reactor. Now here, straight tubular reactor is used. The thing is, why actually the RTD study is required? The reason behind this is the reactors we operate are not ideal in nature. So real reactors has got some non-ideality in them. So to study the RTP, now the question is, what is actually RTP? RTP is distance time distribution. Now, what is residence time? Residence time is nothing but the time for which the molecules of the reactants reside in our reactor. So you can see that in real reactors there is a distribution of the residence time. Now, for the ideal reactors, take that case, and is for Doppler reactor, all the molecules will have the same distance time. That is not true for the real reactors. And that's why we have to study the RTD or the distance time distribution experiments. Now, how do we operate such experiments? So, first of all, these experiments are operated in non-reactive mode because this has nothing to do with the reaction, but this is all to do with the hydrodynamics in the reactor, that is the flow pattern. And if we determine the distance time distribution, you can have the idea about the mixed mix. That is also in the plug flow. In case of real plug flow reactors, there is some mixed component or dispersed component. Now, how to determine this? How to determine the residence time distribution? So you can see here, this is an experiment with a tubular reactor, and here we will inject one tracer in a pulse. What is a tracer? Tracer is a non-reactive pen. That is, this has nothing to do with the reaction, and this should be non-interactive in nature towards the reactants. So we can choose different types of tracer, and we can input or make some input of those tracers in the reactor to have the idea about the business time distribution. Now here, we operated for the input of pulse time. What is pulse input? This is nothing but it is done, the input is introduced into the reactor instantaneously. How is it done? It is done by some injection. We will inject, say here, we will use the sulfuric acid as a tracer. So instantaneously, we will inject some sulfuric acid into the nose stream. So it is first, you can see this apparatus. So here, there is a tank for which holds water. So first, the water will be flowing through this, through the tube, and now at a particular time, you will inject some H2SO4 into the system. And now, when we operate the pulsed mode of experiment, we have to also know the outlet concentrations of the tracer. So from the pattern of the outlet concentration of the tracer with the time, we can have the idea about the RTP. Now you know that there are different types of bugs which can be generated through the RTP function which is very important for the analysis of non-identity is nothing but the ET. ET is distance time distribution function. So how to determine is ET from a first type of tracer experiment. How to do it? So this is a schematic. So this is the reactor. You have injected the H2SO4 in it, and you will take some effluent sample with time from here, and you can determine the ET value from this one. That is, this is actually the equation. So ET is actually VCT. V is the volumetric flow rate times the concentration with time divided by N0. N0 is the amount of the tracer which has been put into the system in the pulse mode. So here you can see that ET you can determine actually from this. That is, ET is actually CT by integral of CT ET with the limit 0 to infinity. Now, we cannot go on doing the experiment for infinite time. So, actually, we will do the experiment for a long time, say 20 minutes, and we will, for the denominator, we will numerically integrate this. So, CT, you will measure the CT values, and from that, you can obtain the ET value, that is the residence time distribution function value. Now, as soon as you determine ET, you can also determine the moments of the RTD or residence time distribution. Actually, the moments will give you the characteristics of the residence time distribution of the molecules in a reactor. So, the determination of moments are very important when you want to compare it with the idle reactors, also for the reactors with having different types of flow patterns. So for the moments, you know that there are three types of moments. One is the first moment, which is nothing but the mean time. So Tn, it is Tn. And Tn is given by integral of T ET divided by integral of et dt in the limit 0 to infinity. Now you know that integral of et dt in the limit 0 to infinity is nothing but 1. So it ultimately converges to integral of t et dt in the limit 0 to infinity. So here also infinity we cannot do the experiment for infinite time. So as I already told that for the reaction time of say 20-30 minutes, you will
ম্যাম
do the
প্রেজেন্টেশনটা দেখা যাচ্ছে না।
ম্যাম আপনার প্রেজেন্টেশনটা বন্ধ হয়ে গেছে।
integration to evaluate the value of Tn or the mean time. Now there is another moment which is called the second moment of RTD, and this is nothing but the variance. Now how to calculate the variance? You can see sigma square. This is nothing but the integral of t minus tm whole square. The tm you have already determined. So t minus tm whole square et dt in the limit 0 to infinity will give you the value for the variance or the second moment of the RTD. Similarly, it is also important to know the third moment of the RTD, which is nothing but the skewness. And skewness is defined by 1 by sigma to the power 3 by 2 into integral of t minus tm whole cubed et dt, and the integration limit is 0 to infinity. And in the similar manner, you can also find out the skewness factor, that is the third moment of RPD. And usually these three are sufficient for the characterization of the Descriptive type distribution for a reactor. So I think you will see the demonstration and how to operate it, and then your knowledge will be more clear. Thank you. The tank is filled with water, and now this fluid will be flown by the use of compressed air, and so this tank is actually attached with the compressor line, and you can see the rotameter over here. We can set the fluid. Okay, and you can see that water is flowing from here. You can see the water is coming out from here. So after say 5 minutes, we will inject the tracer from this point. Introduce the tracer from here. You can see the tracer is injected. Now we will go to this point. So I'm taking sample from here and putting it in the conical flask for titration. So 10 ml of samples are being drawn. That means if you titrate these samples, you can get the CT values, the concentration of H2SO4 from here. So from the values of CT, you can directly draw the C curve by plotting CT against T. And also I have already told you how to determine ET and all the moments. So by following those procedures, you can determine the values of ET as well as the mean time, the variance and the skewness. After the experiment is over, please set your rotometer to the null position, that is the zero position, and depressurize the system. So you release the pressure from here. Depressurize the tanks. And switch off the compressor. That's all. The experiment will be repeated for 3 fluorides to check the RTD pattern of the reactor. 5, 10, and 15. Yeah. So, is there any doubt? I think in the physical class, I'll also show you again. Have you understood the experiment? Have you understood?
হ্যাঁ ম্যাম, বুঝতে পেরেছি।
ঠিক আছে।
ম্যাম,
Physical
আমাদের
class
অফলাইন ক্লাসটা চালু হলে কি ম্যাম আমরা একবার করতে পারবো এগুলো, মানে নিজেরা?
দেখা যাক, তোমাদের আরো 4টে এক্সপেরিমেন্ট বাকি আছে।
আচ্ছা আচ্ছা।
তোমাদের সিএসটি এর বাকি রয়েছে, পিএফআর, পিবিআর আর সেমি ব্যাচ, 4টে এক্সপেরিমেন্ট এমনি বাকি রয়েছে।
ম্যাম নেক্সট উইক থেকে যদি অফলাইন শুরু হয় দেন এটার সাবমিশনটা কিভাবে করব, মানে ক্লাসরুমেই
নেক্সট
নাকি?
উইকের মধ্যেই করবে। হ্যাঁ, সাবমিশনটা ক্লাসরুমে করে দিতে পারো, কিন্তু এই ক্লাসটা অবধি তো অনলাইনে হলো, সাবমিট একটু থ্রু অনলাইন অনলি, অ্যান্ড তারপর দিন থেকে রিপোর্ট শিট নিয়ে
Ma'am,
So
can we submit next to next week, ma'am? Actually, ma'am, most of them are, ma'am, like me. I'm from outside of the Kolkata, so ma'am, I will be needing a time for relocation and all, and many of them will be needing a time. So we can submit after next to next week.
but you will submit online only. So you can
Actually,
make
ma'am,
it by the this weekend, the next weekend, not next to
ma'am,
next.
we will be like traveling, and we will have to look for, ma'am, PGs and all.
We
So,
have to
ma'am,
look for our PGs and we have to shift
Okay,
our
okay,
whole
I understand that.
so I
Okay,
setup as
think,
okay,
well.
ma'am, if you can do
okay,
it next to next week, it will be, ma'am, very.
okay, okay, no problem. Okay.
Thank you,
Thank
ma'am.
you.